for our notes on identifying bases and learning about pH and pOH and how to do calculations with those. All right. We've had a few people away the last few days, so I'm making a set of notes so you can follow along at home, because I would say it's pretty tough to miss the beginning of a unit. All right, so order of the day here is we're going to see if we can learn how to identify strong and weak bases, how we can use our relative strength of Bronsted-Lowry acid-base sheet to figure out what bases could be. And we'll come back to that. We're also going to learn to perform calculations involving pH and also calculations involving this thing called pOH, which is a thing. Okay, so let's start by figuring out how we know if we're looking at a strong base. So to remind you, we know how we're looking at a strong acid. They're these guys. They have special names. You might have even heard of them in movies and stuff like that, sulfuric acid and what have you. Pretty common, a few of these, in everyday language, especially hydrochloric acid and sulfuric acid. And the rest are non-strong acids. Okay. So for strong bases, what we're really looking at is a salt that either contains a hydroxide ion. Of course, that's the sort of ion that contributes to alkalinity or basicness. So we want either a hydroxide ion or an oxide ion, which is an O, two negative charges on it, an oxygen with two negative charges, or an NH2 ion, which for the moment the name escapes me. I think it's azide ion or something like that. Anyway, so some examples are like, say, sodium hydroxide. So I'm making a salt that contains it, and so I balance out that negative charge with a positive charge of a sodium and lithium hydroxide. Now what's key here is these examples of hydroxides, well, we've chosen values that are soluble with hydroxide. So when you put them in water, they dissociate entirely, because that's a strong base, right? Everything dissociates or ionizes. So calcium oxide as well, which is called quicklime, would be an example of a salt that's bound with our oxide ion. Now if we look at the bottom of our Bronsted-Lowry table of acids and bases, acids on the left, and their bases are actually on the right in this column here. Now, unlike the acids where we start strong at the top, we actually start weak right here, which means these guys don't even act like bases. There's in no way do they ever accept protons to turn back into these. In no notable way at any rate. And so we start with water as our weakest base. As we talked about in 4.1, water can act as a base or an acid. Okay. And as we progress down, we get to our strong bases. And you can see these bases here, our NH2, our oxide ion, and hydroxide. And these guys, if they're in some sort of salt that you add to a solution, that acts as a base. Then they'd be strong bases. So let's talk about why. Pretty simply, because NaOH, sodium hydroxide, will dissociate entirely into sodium ions and hydroxide ions, and this occurs 100%. That means that the number of moles of sodium hydroxide for every liter that you started with is equal to the number of moles of hydroxide for every liter that we start with. So when we're done, the concentration of hydroxide ions is is actually the same as the concentration of our sodium hydroxide. And it's kind of similar to our acids that we saw earlier, actually. The concentration of the hydronium was equal to the concentration of our original base salt, or acid salt in that case. Now, there's one trick here with the hydroxides, though, which is that, let's take a look at the dissociation reaction for barium hydroxide here. We have a barium ion and hydroxide ion. But there's, of course, two hydroxide ions, and so there's a little bit of wrench in the works there. So if you had 1.0 molar barium hydroxide, we'd actually have twice the number of hydroxide ions that we would barium ions. So 0.20 molar hydroxide. And so then we have this principle that for strong bases, the concentration of hydroxide is equal to the concentration of your base, or salt, right, times the number of hydroxides in the formula. In this case, there's two hydroxides in the formula. And I imagine you could think about a situation where there might be three. Okay. And also salts that produce oxide ions and azide, NH2 negative ions. They also act as strong bases, but they don't produce OH directly. They produce it indirectly. So let's look at how these are produced indirectly. So the first thing we want to think about, if we're putting, say, CaO, calcium oxide, into water, is that it dissociates like normal. And it produces this guy, which is a very strong base. Or rather, it's a very strong base component of quicklime. All right, but then what happens? Well, this guy's floating around in water, and it's going to steal a proton from water, act as a base, which means it accepts protons, and water, in this case, will act as an acid, donating a proton. So as a result, when this guy gains an H, it becomes an OH, and we have two negative charges and one positive charge, which gives us a negative charge overall. And when this H2O loses a proton, loses a hydrogen, we lose a hydrogen, we get an OH, but also it loses a positive charge, leaving it with negative. So actually that means we have two hydroxides for every one calcium oxide we add to water. All right, so to find the hydroxide concentration in, say, a 0.10 molar calcium oxide solution, well, we would start by saying, okay, well, if I have calcium oxide, and that all turns into calcium ions, or oxide ions, oxide, thank you. Well, I know that if I start with 0.10 molar of calcium oxide, I'm going to end up with 0.10 molar solution of calcium ions because it's a 1-to-1 ratio. But it's a 1-to-1 ratio as well of oxide, so I'll have 1.01 molar oxide solution. However, if I look at this solution here, this reaction here, I have an oxide ion, which will mix with water. It's going to steal a proton, and actually, as a result, just as we talked about, it's going to create two hydroxide ions. Okay, so if I had 0.10 molar of my oxides, I'm going to actually have twice as many hydroxides. Now there's plenty of water, so it's actually irrelevant. The number of moles of liter per number of moles of water for every liter of water is quite high. It's like 55 mole or something like that. And it doesn't change significantly in a reaction like this, so we're going to ignore that for now. All right, so the hydroxide ion concentration is 0.20 molar as a result. Okay. So that's identifying strong bases. They're the bases that have salts have a hydroxide, or maybe an O2 minus, or an H2, which is pretty rare. All right. Now, weak bases, as you might have already guessed, are all the bases that are not considered strong bases like these guys. That's everything above, and really a salt that you can make in combination with these. All right. And so we're going to be looking for salts that contain ions above hydroxide on the acid-base table. And so this is sort of an approximation of the acid-base table. These are the strong bases here. And we're looking at everything from phosphate ions and above. And so you can take any of these and mix it with, say, 3 Na plus ions, and as a result make a weak base, PO4 3 minus. Oops. And so this is an example weak base. Sometimes we actually call the ion itself the base. It depends on context. And sometimes we call the salt a base. And so we have to be flexible to flip back and forth there. So I chose some random negative ions from the base side of this table, like iodate, I believe it's called. Yeah. And this guy, acetate, and balance them with positive ion charges. So sodium iodate or lithium acetate, and so on. There's many different weak bases we could think of. And so that's how we know we have weak bases. Okay. So let's get on to talking about pH. All right, so for pH, I'm going to want a nice, powerful calculator that has a very clear log button. Here we go. Cool. All right, so pH stands for something, actually. It stands for the power of hydrogen. Power of hydrogen. And what it really means is the power of the concentration of hydronium ions in solutions. And when I say power, the way we convert that into math is actually using a button that you probably haven't used in math before. It's called the logarithm button. And that helps turn things into logarithmic scales. And so you know pH is a way of taking concentration, and each increment of a number during pH means a 10 times increase in concentration, or decrease in the case of a log scale, because it's a negative log scale. All right, anyways, so it's this math function which is performed on the concentration of the hydronium ions in a solution. Okay, so very simply, we may be asked to say find the pH of a solution that has some hydronium ion concentration. So the pH is really just equal to negative log, and we're not going to have time to talk in too much detail about what a log is, or logarithm is, and how it works and why. But if you're taking pre-calculus 12, you'll have some time to unpack the idea of a logarithm in more detail. We're just going to use it as a tool to do what we want it to do for us. So the way this works is we press the negative button and find our logarithm button, which is right here. And we're going to open a set of brackets and just write in our value, 5 times 10 to the power of negative 12. And we'll just get some number out of it. Oh, we get 11.3. Oh, I put 12 instead of 3. I don't know why. I don't know where I got 12 from. So I'm going to go back and edit that because I'm too lazy to rewrite it. And we get 3. And that should actually be 2.3. Okay, so the pH, if you have that concentration of hydronium, is 2.3. Okay, it's pretty straightforward. Now, however, of course, we have to know that in a 0.0 whatever concentration of HCl, we have to know that this means we have a 0.00021 molar concentration of hydronium ions as well, right? That's something that we covered when we talked in 3.2. And by 3.2, I mean 4.2. That's something we talked about back here, right? We had this idea that in the strong acid, the concentration of hydronium is equal to the concentration of the acid itself. So, if this acid had a concentration of 21/100,000ths of a mole in a liter, then that's the concentration of hydronium ions, because this is a strong acid. If HCl wasn't a strong acid, this wouldn't work. All right, so that means we're going to find the pH by taking the negative logarithm of that value. And very simply, we just write a negative log of 0.00021. That gives us 3.677. So pH equals, I'm going to call it 3.7. All right, I need to take a break and drink some water. All right, we can do a similar trick here with this next question. We know that the concentration of hydronium ions is the same thing as the concentration of the acid, which means it's going to be 6.0 molar solution. So to find the pH, we'll just take the negative logarithm of 6.0. But the calculator won't know we're putting in 6.0, we'll just put in 6. Because it's the same number as far as the calculator is concerned. And we find that a 6 molar concentration has actually a quite strong negative pH. It's negative 0.8. So the pH is negative 0.8. Oops. pH equals negative 0.8. All right. And that would be acidic. That would be more acidic than stomach acid, for example, by a factor of maybe about 100 times more acidic than stomach acid. All right. So this is really important here. We have a way of converting now from hydronium ion concentration to pH. So to go from one to the other, we take the negative logarithm of our hydronium ion concentration. However, to turn from pH to concentration of hydronium, we must be able to do something that does the opposite. This operation has an inverse, and the inverse is 10 to the power of negative pH. So this is all reversible. If I want to take some pH and find the concentration of hydroxide ions, hydronium ions, pardon me, I take 10 and I raise it to the power of the negative value of our pH. So for example, I had a negative pH here. Now this gets a little funky unless we keep some extra decimal places for the pH. So I'm actually going to say 0.778. And I'm going to say, okay, if that's my pH, then I have to put 10 to the power of negative 0.778, which is what it was before I rounded to negative 0.8. Oh, and we had the negative pH, but the negative version of a negative number. Okay. And then we get 5.998 and so on. And you can tell if we rounded a little bit more, we kept a few more decimal places than 3, we might get an even closer number to 6, but I hope you see how 5.9979 is approximate to 6, especially with the number of sig figs we have there. This would round, if we rounded to 2 sig figs, to 6.0. Okay, so we'll talk about how we can use that inverse to perform the opposite operation. So the opposite operation might say, okay, you have a pH, like we're asking for the hydrogen ion concentration of blood. It has a pH of 7. So we know that the hydrogen ion concentration is equal to 10 to the negative pH. So we'll just put in our pH in place here, so negative 7.4. So what's the pH of blood? It's 10 to the power negative 7.4. And it's small. We get 3.98 times 10 to the negative 8 molar. Now, that should make sense because the hydronium ion concentration in a basic solution is probably pretty small. And it turns out it is. Let's move on. We could also be asked to take it one stage further. We're not asked for the concentration of hydronium anymore. We're asked for the concentration of sulfuric acid, and we know that we have a pH of 3.7. So first, I'm going to find the concentration of hydronium because I know that can be done using this conversion, 10 to the power negative pH. And I know my pH is 3.7. So we'll find out what 10 to the power of negative 3.7 is. And we get some pretty small concentration. It tells us that we have 1.9. That's like 2.0. I'll just round it to 2.0 times 10 to the negative 4 moles for every liter. And that's hydronium ions, right? Concentration of hydronium ions. So what we need to know is that this sulfuric acid turned directly into hydronium ions when it mixed with water, of course, and made some, I forget what this is called, hydrogen sulfate, probably, something like that. It doesn't really matter. But what matters is that this is unidirectional. It's a strong acid. This is going 100%. So whatever the concentration of hydronium is equal to the concentration of our acid, our strong acid, only with strong acids. And sulfuric acid is a strong acid. Okay. So that means the concentration of sulfuric acid is equal to 2.0 times 10 to the negative 4 molar. Okay. Now, we'll move on. We'll talk about this more funky new term called pOH. So pOH is really similar. Just like pH gives us a negative logarithm of the hydronium concentration, or like the power of hydrogen, this is the power of hydroxide. It tells us we get the negative logarithm of hydroxide. So in a very similar way, to find a pOH, we really just take a hydroxide concentration and we just take the negative logarithm of it. And to return backwards to our hydroxide, we're going to take 10 to the power of the negative value of our pOH. Okay, so let's see how pOH works. So if I know I have a hydroxide concentration of 3.6 times 10 to the negative 5, my pOH is equal to the negative logarithm of 3.69 times 10 to the negative 5. Negative logarithm, 3.69 times 10 to the negative 5. Oops. What's wrong? Quite out of syntax there. Negative logarithm. 6 times 10 to the negative 5. Oh, this is a little closed bracket with no open bracket. All right, we get a pOH of 4.4. That's kind of like a pH. We'll talk about how they're connected in a second because it's actually pretty important how pH and pOH are related. All right, lastly, we'll find out what's the pOH concentration of a solution with what's the concentration of hydroxide of a solution with a pOH of 13.7? All right, so again, we know that pOH, to get a hydroxide concentration, we just take 10 and raise it to the power of the negative value of our pOH, which is to say that our hydroxide concentration is equal to 10 to the power of negative 13.7. So 10 to the power of negative 13.7 gives us a very small concentration indeed. The concentration of hydroxide is so small, I guess it's 2.0 is how that would round, times 10 to the negative 14 is so small that I don't know if you'd have very much luck ever detecting that hydroxide in a solution. You could detect it indirectly, but probably not directly. It's so small, that pH. Okay, pOH I meant. All right, so what is this pOH thing anyway? Okay, we learned how to use it, but what's a pOH scale like? And how is it different or similar to a pH scale? Well, we need to know that pH and pOH together just add to 14. So you can picture a pH scale. Well, pOH scale is the same, just reversed. So that means if pH is 1, like in the stomach, then pOH is 13. It's a component. And in a neutral solution of pH 7, pOH is also 7. Okay. So if I know a pH and I want to find a pOH, all I do is I take 14 and I take away my pH. And that takes us to pOH. And similarly, if I have pOH and I want pH, I take 14 and I take away my pOH. And we can see it works both ways, right? If my pOH of a solution is 13 and I want my pH, I just take 13 away from 14 and I get 1. Okay. Now also, we already know how to take a hydronium ion concentration and turn it into a pH. That's a negative logarithm of our hydroxide concentration. Pardon me, our hydronium ion concentration. And if I want to go from pH back to hydronium ion concentration, I do 10 to the power of negative pH. And there's a pretty similar path that we take when we're dealing with going from pOH to OH. We do 10 to the power of negative pOH, as we talked about. And again, when we reverse, we go negative logarithm of our hydroxide concentration. Okay. So this is our inner path. This is going in one direction as we go from hydroxide ion concentration to pH. We can go from pH to pOH. We can go from pOH to hydroxide concentration. Now, we could probably go from hydroxide ion concentration to hydronium ion concentration. And we can, but in order to do that, we need to know one other thing. We need to know this last fact up here, which is that as long as it's 25 degrees, the concentration of hydroxide times the concentration of hydronium ions is 10 to the power of negative 14. So if I have my hydroxide concentration, I need my hydronium concentration, I just take 10 to the power of negative 14 and I divide it by my hydroxide concentration. And we can do the reverse as well. It's the same principle. When I want to isolate my hydroxide concentration and I know my hydronium ion concentration, I divide both sides by 10, by my hydronium concentration. So I get 10 to the power of negative 14 divided by my hydronium concentration. Okay. And we'll see if that can help us at all. Alright, so if we know we have some hydronium concentration, that's 5.04 times 10 to the negative 3, we are starting here And we can use this hydronium ion concentration to find our concentration of hydroxide, our pH, and our pOH. So I'm going to start with finding the hydroxide concentration. So to find our hydroxide concentration, starting here, we're just gonna say, okay, so I actually like to start from base principles. I don't really I find using these sorts of diagrams can be a bit of a crutch. I like to start from base principles personally. I like to say, okay, well, I know my hydronium ion concentration times my hydroxide concentration is equal to 10 to the power of negative 14, assuming we're at 25 degrees. And if it doesn't say so, I'd like you to assume that it does. And let's see what we know. I know my hydroxide ion concentration. So that's like saying I have 5.04 times 10 to the negative 3 moles for every liter. And that's multiplied by my hydroxide concentration. That's equal to 10 to the power of negative 14. So if I want my hydroxide concentration, I should divide both sides by 5.04 times 10 to the negative 3 molar. And we'll divide this one by 5.04 times 10 to the negative 3 molar. Now, we should probably ignore the units in this case. These guys actually just cancel out, but this gets into an important idea about what the units of this value are, and that's an interesting question, and we'll get to that. But right now, we're not going to deal with it. All right. So this has a result of canceling out. Where's my red pen? My red canceling pen. My 5.04 times 10 to the negative 3 on both sides. And I end up just isolating my concentration of hydroxide, which is what I was asked for. That's equal to 10 to the power of negative 14 over 5.04. 10 to the power of negative 14 divided by, I'm going to open up a set of brackets to make sure everything goes in nicely, 5.04 times 10 to the power of negative, what was it, negative 3. All right, I get 1.98 times 10 to the negative 12. And I should know that in my concentration of solute should be in molar, or moles per liter. Okay. So now I need my pH. So what do I know? I know that for pH, I have this principle that says my pH is defined to be the negative logarithm of my hydroxide concentration. Okay, so since I know my hydroxide concentration, I should be able to find my pH. It's a negative log of 5.04 times 10 to the negative 3. All right, so negative log of, open bracket, 5.04 times 10 to the negative 3. And we get a pH of 2.30. 2.30. All right, and lastly, we'll need the pOH. So to find the pOH, I have two options. I could use my hydroxide concentration, or I could use the fact that pOH and pH at 25 degrees Celsius add to 14. Okay, so I'm going to do both, actually. First, I'll say my pH plus my pOH must equal 14, and I know my pH is 2.30 plus my pOH. It's going to be equal to 14. Oops. And then I'll just take away 2.3 from both sides. And that tells me that our pOH is equal to 11.70. ish. All right. And let's just see if I can do the same thing here. Or I could use pOH is equal to the negative logarithm of my hydroxide concentration. Now, since we found the hydroxide concentration in the first portion here, I hope we're going to get a very similar number for our pOH, 1.98 times 10 to the negative 12. So this is going to come down to how well we rounded in both of these steps. So let's find out here. Negative logarithm of 1.98 times 10 to the negative 12. Delete. 11.70. Hey, look at that. It's the same number. So the pOH equals 11.70. All right, that's good that they agree. I was expecting to be a little bit off the decimals, but it looks like things worked out okay. All right, so these are skills we can use to answer practice questions, which are on the back here, 4.2 and 4.4 self-test. All right, so good luck. I hope that helps a little bit. And I'll be putting up the solutions to the self-test at a later date, probably Friday.